And we are here to present our progress on a low-cost Aerospike nozzle for a hybrid rocket motor. So the motivation behind our project is to create an Aerospike nozzle that will outperform a conventional de Laval or conventionally known as a conical nozzle. This nozzle will be integrated into a hybrid rocket motor, and that motor will be used into for a rocket competition rocket in the intercollegiate rocket engineering competition. The goal for this competition is to achieve an altitude of 10,000 feet while flying a 30-pound scientific payload. So a quick introduction into nozzles. Nozzles are typically optimized for a specific altitude. What this means is that the ambient pressure and the exhaust flow pressure are equal to each other, thus creating the most optimized and highest efficiency of the nozzle. What this means is anything above or below the specified altitude, the nozzle is actually losing efficiency. So at low altitude conditions, we have an underexpanded scenario where the ambient pressure is actually higher than the exhaust flow pressure. And this kind of squeezes the exhaust flow, reducing our efficiency. And then in the other end, we have lower ambient pressure than the exhaust flow pressure. And this creates an overexpansion where the exhaust flow is overexpanding past the dimensions of the nozzle. So this is where our Aerospike comes into play. The Aerospike actually takes advantage of the ambient pressure in an underexpanded condition, and it'll squeeze the exhaust plume onto the Aerospike, thus increasing our thrust and our overall efficiency. And then in an overexpanded condition, there's shock waves that are created from the Aerospike that reduce the overexpansion of the nozzle, or the exhaust plume. So we don't lose as much efficiency as compared to a conical nozzle. So in the 1960s is when a lot of research was being done for Aerospikes. A company called Rocketdyne took their J2 engine out of the Saturn V rocket and replaced the bell nozzle with an Aerospike nozzle. The performance of the Aerospike was very similar to the bell nozzle. Then in around the 1970s, they created the XRS 2200, which is a linear Aerospike nozzle. This nozzle was actually designed for single stage to orbit aircraft or spacecraft. However, not much research has actually been done to further the single stage to orbit spacecraft. The most recent example of an Aerospike nozzle is from a company called Firefly, and they have their Alpha rocket, and their goal is to create an economic means to get light satellites into low Earth orbit. So I'm going to hand it over to Joe, and he's going to briefly go over some of the standards that we've implemented into our project.
Okay, the applicable standards that we have for our rocket deal with the TRA Research Safety Code and the National Fire Prevention Association Safety Code. And they essentially say that the casing that we use can't be made out of frangible material, so it won't explode when it ruptures. In addition to that, the rib closures can't be made out of that steel material either. In our design particularly, we had to actually limit the amount of steel as due to the construction of Aerospike nozzles, they can't be made completely out of aluminum or graphite. All right, in addition, there's requirements for our solid propellant as well, and it has a specified auto ignition temperature of 125 or higher. The casing can't get higher than 200 degrees Celsius, and the liner has to be 28 millimeters or more. In addition to that, the motor failure has to be in an axial kind of mode. It can't fail in hoop because they're worried about fragmentation. Now it turns over to Amr for design alternatives.
Thank you, Joe. So for our first alternative design, we have the dual bell nozzle, which was first considered by JPL in 1949. And the dual bell nozzle accomplishes its altitude compensation with something called nozzle wall inflation. Basically what that is the change in the wall's shape, as you can see here in the figure we have. And what that offers is that it offers controlled separation under sea levels. However, some of the main disadvantages that we face using the dual bell nozzle is the overexpansion that we get. And this causes a lot of thrust loss. It limits the efficiency of the motor or the engine. And also, you may interact some of high frequency wobbles, which is very dangerous. Our second alternative design is the ED nozzle, or the expansion deflection nozzle. And while it looks and works much like a bell nozzle, the main difference that you can see over here in the figure we have is the plug that's positioned in the upper part of the nozzle. And basically what that plug offers is that it pushes or forces the flow that's going from the engine into the walls of the nozzle. And however, this creates a very big disadvantage when using this nozzle. And as you can see here, it creates a void in the middle of the nozzle, which causes something called an aspiration effect. And this eventually causes an overexpansion and all the disadvantages that we mentioned previously come with it. So for our third alternative design, we have the truncated Aerospike, and the truncated Aerospike is basically like the full Aerospike that we're using, with exception to the presence of the spike itself. And with the absence of the spike, you get less efficiency or less performance for a given distance in comparison to a full spike that we are using. Also, the flat plug that we have here creates a turbulent wake in the bottom of the nozzle, which creates like a turbulent kind of effect and reduces the efficiency on the nozzle. And for our final design, we have, next slide please. For our final design, we have the Aerospike, which is basically named for its notable spike that's in the middle of the center body. And this spike, in our opinion, creates the most efficient or the most perfect design to use because, as I said before, it will give you a better performance for a given distance in comparison with its truncated version. Also, the Aerospike is much smaller in sizing compared to a dual nozzle for the same performance that we get from both of them. And then the Aerospike nozzle, its engine is much smaller, it's efficient, and it's easier to use and much safer for a design, which is perfect for a design. And finally, we have a comparison for all our alternative designs with the full Aerospike nozzle that we are going to be using. And if you look at the chart, you will see that the full Aerospike version comes on top in almost all of the features that we have. And now I'm going to hand it out to Joe for the final conceptual design.
All right, our final conceptual design utilizes a standard 54mm motor mount, which means that most conventional commercial nozzles this kit will retrofit into. Our test motor will also be able to fit into standard 54mm motor mount rockets as well. We're expecting to see about a 5% increase in efficiency just on overall on the Aerospike itself. And we're intending this design to be paired with a conventional K800 reload made by Cicerone Motor Technologies. Our experimental plan is we're going to be doing static hot fires with APCP grains. We plan on manufacturing a conical nozzle as a control to test against our Aerospike nozzle. In addition, we're going to also be using a load cell that deflects as you apply force to it and calibrating this so that we can get very accurate and very detailed measurements of thrust comparing the two different nozzles. Additionally, we're going to do a series of control tests that basically test how well the nozzle expands and deals with high heats and possible two-phase flow that we're going to be going through it. Here we have a rough cost analysis. We expect the initial prototyping cost to be about $750, but we expect our projected manufacturing cost to be around $150, which puts us right about in line with the majority of commercially manufactured motors and what they cost for nozzles. Now I turn over to Shane for our timeline.
So the majority of the semester is our time's been given into coming up with the design of the actual Aerospike. As Amar mentioned, we came up with some alternative designs and hashed out the advantages and disadvantages of each design. And now that we've actually selected the full Aerospike, we've gone into the simulation phase to actually test whether our design is feasible or not. And we have to refine our design based off of those simulations. Then moving into the summer, we're going to be looking for sponsors and ordering parts and begin our assembly and manufacturing. We need to lean out our manufacturing in order to keep costs down. And then once we have a final prototype, we'll be moving into the fall semester. This is where we're going to take our prototype and begin coming up with our testing procedure and refining the testing procedure. Then look at our data, analyze the data, and then present that the overall consensus of the nozzle in December. So some of the global element designs that we included into our project include using SI units that are globally known and easily recognized. Also, for our instruction manual to actually install the Aerospike, we're using more of a pictorial method, kind of similar to IKEA sort of format. Very little words. That way anybody can get the nozzle and intuitively know how it's supposed to be installed into the retrofitted motor. And as Joe mentioned before, we're using a 54mm adaptation. So there's only so many rocket manufacturers in the world, and they all use about the same standard sizes. So we selected a standard size that the manufacturers are already using. So as I previously mentioned, we are still doing our simulations to finalize our design, and then we'll be moving into the production and manufacturing phase. Once we have our final design or prototype created, we're going to move over to testing. And then once we have a proof of concept, we're going to take that nozzle and install it into our IREG rocket for the 2017 competition. So this concludes our presentation. We want to thank you for giving us your time, and at this moment, we'll take questions.
Thank you.
All right. So you guys are going through multiple iterations with your simulations here. What are some of the items that you are changing from simulation to simulation?
One of the ones that we're changing simulation to simulation is the actually outer shape of the spike shell itself. So the actual inner profile of the Aerospike nozzle is actually determined by a program that we've run into. It's actually just called like Aerospike Sim like 2.21. But the actual outer closing shape is actually somewhat flexible. So that's one of the things we're changing in iterations, as well as the length of the spike is actually also variable. So if you make it longer, it's a little bit more efficient. But as you make it shorter, it's less efficient. But it's suddenly becomes more durable, easier to handle, cheaper to manufacture. So it's finding a balance on those that we're comfortable with.
And you guys have set up then for yourselves clear metrics or clear goals that you're looking for those items?
One of the ones that we haven't set up, we have most of them set already. One of the ones we haven't quite determined is impact strength to the spike from the bottom. As it will be on a launch vehicle, it typically does land tail first. Trying to find some way of actually shielding the actual spike itself is kind of proving a challenge. But we may resort to like some kind of external shell, so that it's not really a concern. We're then just limited by like how long do we actually want to make kind of an outer tube that sits on the rocket itself.
Any other questions?
Thank you.
Thank you.